Hey, did you know that lead pencils actually don't contain any lead at all?
That's right. Lead pencils contain graphite encased in a wooden covering. Graphite is nothing but carbon. In fact, carbon is found practically everywhere in your surroundings. It is present in the clothes you wear, the food you eat, the fuel in your car, and in the tissues of all living beings. No wonder, carbon is the sixth most abundant element in the universe. This lesson is about the different forms that carbon takes. By the end of this lesson, you will be able to explain the significance of carbon in our daily life, list examples of the occurrence of carbon in nature, define allotropy, describe the different allotropic forms of carbon. Carbon is one of the few elements that can exist free in nature. In the free state, carbon occurs as diamond, graphite, fullerene, and coal. In the combined state, it can be in the form of a gas. For example, carbon dioxide and carbon monoxide. Carbon can also take the form of a liquid in the combined state. For example, petroleum and vegetable oils. In the solid form, carbon occurs in ores such as limestone, magnesite, dolomite, and calamine. Allotropy is the property of an element that allows it to exist in more than one form. In each of these forms, the chemical properties will be more or less similar, but the physical properties will be different. The allotropes of carbon are classified into crystalline forms and amorphous forms. The black residue left when carbon compounds are heated is called amorphous carbon. Diamond, graphite, and fullerenes are crystalline allotropes. Coal, coke, wood charcoal, animal charcoal, lampblack, gas carbon, petroleum, and sugar charcoal are the different amorphous allotropes of carbon. In a diamond, each carbon atom is bonded to 4 other carbon atoms by a single covalent bond. This is why a diamond is a rigid, compact, three-dimensional structure and is very hard to break. It is a bad conductor of heat and electricity as there are no free electrons present in it. Graphite contains carbon atoms in hexagonal rings, and the rings in turn are joined together to form a layer. A series of such layers are piled one over the other. The layers of carbon can slide over each other because there are no strong covalent bonds between the atoms of 2 adjacent layers. Since graphite contains free electrons, it is a good conductor of heat and electricity. Fullerenes were discovered in 1985 by Robert Karl, Harold Kroto, and Richard Smalley, for which they were awarded the Nobel Prize for Chemistry for the year 1996. A fullerene molecule consists of 60 carbon atoms arranged in pentagons and hexagons, like in a standard football. Fullerenes are also called Buckminster fullerenes as they are shaped like the geodesic dome designed and built by the US architect Buckminster Fuller. Carbon compounds are all around us. In our clothes, furniture, food, and body. To understand why carbon forms so many compounds, we need to look at bonding in carbon. In this lesson, you will learn about bonding in carbon and the different types of covalent bonds. At the end of this lesson, you will be able to list the properties of covalent compounds, explain the reasons for each of the properties of covalent compounds, list the steps for writing electron dot structures, classify the different types of covalent bonds, and explain covalent bonding in carbon with reference to methane. Covalent compounds are identified by some distinguishing properties. Let's look into the properties of covalent compounds. Covalent compounds have low melting and boiling points. This is due to weak forces of attraction between the molecules. For example, chloroform has a boiling point of 60 degrees centigrade. When compared to ionic compounds, covalent compounds are non-conductors of electricity. This is due to the absence of free ions. The type of bonding in the carbon compounds does not give rise to any ions. To understand the bond formation in carbon, we need to know the combining capacity of carbon. The combining capacity of any element depends on the number of valence electrons. Therefore, in order to know the combining capacity of carbon, we need to know the number of valence electrons in carbon. When we look at the electronic configuration of carbon, it is clear that it has to either gain or lose 4 electrons to attain noble gas configuration. Suppose carbon gains 4 electrons, it would form a C-4 ion. But carbon, being a comparatively less electronegative element than fluorine, chlorine, oxygen, etc., is unable to hold 4 extra electrons, meaning it would be difficult for the 6 protons to hold the 10 electrons. Now, suppose it loses 4 electrons, it would form a C+4 cation, which is again a difficult task. It would require a great deal of energy to remove 4 electrons, leaving the cation with 6 protons in the nucleus and holding only 2 electrons. This makes either of these possibilities difficult. Carbon overcomes this difficulty by sharing its electrons with other atoms of carbon or with atoms of other elements. We know that sharing of electrons results in a covalent bond, and the shared electrons belong to either of the atoms. This sharing helps in achieving noble gas configuration. The Lewis dot structures provide a picture of the bonding in molecules in terms of the shared pairs of electrons and the octet rule. A Lewis structure is a type of shorthand notation. In this method, atoms are written using their element symbols. Lines are drawn between atoms to indicate chemical bonds. Single lines are single bonds. Double lines are double bonds. Triple lines are triple bonds. Dots and sometimes the symbol X is used to represent an electron. Steps to draw a Lewis structure. Let's take carbon dioxide as an example in writing the Lewis dot structures. The first step in writing an electron dot structure is to locate a central atom. The central atom is the one with the lowest electronegativity. In carbon dioxide, since carbon is less electronegative than oxygen, it is the central atom. After selecting the central atom, connect the other atoms to it with a single bond. We may change these bonds to become double or triple bonds as we progress. So, let us connect the 2 oxygen atoms with a carbon atom through single bonds on either side of it. The third step is to determine the number of valence electrons possessed by each atom in the molecule. In a carbon dioxide molecule, a carbon atom has 4 valence electrons and an oxygen atom has 6. Now the octet rule states that atoms with 8 electrons in their valence shell are stable. Hence, we need to check if the octet is satisfied for each atom or not. The next step is to arrange the electrons so that each atom contributes 1 electron to a single bond. Now, in the present example, when such an arrangement is done, we can see that there are 6 electrons around carbon and 7 around each oxygen atom. This means that the octet is not complete. As the octet is not complete, move 1 electron per bond per atom to make another bond. In this example, we observed that the octet was not completed. Hence, we move 1 electron for each, and now we see that both the carbon and oxygen atoms achieve the octet by forming a double bond between them. In a covalent bond, a shared electron pair is known as a bond pair. The bond pair is represented by a line between the bonded atoms. Depending on the number of electrons shared between the atoms, the covalent bonds are classified into 3 types: single covalent bond, double covalent bond, and triple covalent bond. Let's look at the formation of a single covalent bond, taking the example of a hydrogen molecule. We know that the atomic number of hydrogen is 1. Hence, hydrogen has 1 electron and it requires 1 more electron to attain the nearest inert gas configuration, which is helium. To achieve this, each hydrogen atom contributes an electron to form a single bond. Thus, a single covalent bond is formed between the 2 atoms of the hydrogen molecule. Considering the example of oxygen, let's see the formation of a double covalent bond. The atomic number of oxygen is 8 and it requires 2 electrons to achieve the nearest stable inert gas configuration, which is neon. To achieve this, 2 oxygen atoms contribute 2 unpaired electrons to produce 2 bond pairs. Thus, they share these 2 electron pairs to form a double bond or dicovalent bonds. Let us try it with nitrogen. The atomic number of nitrogen is 7 and it would require 3 electrons for attaining the nearest inert gas configuration, which is neon. Thus, the 2 nitrogen atoms combine together and produce 3 bond pairs and share the 3 bond pairs between them. Thus, a triple bond is present between the 2 nitrogen atoms in the nitrogen molecule. Now, let us take a heteroatomic molecule like methane and see the covalent bond formation in it. A carbon atom has 4 valence electrons. During the formation of a methane molecule, 1 electron of a carbon atom pairs with 1 electron of a hydrogen atom to form a bond pair. In this way, 4 bond pairs, which are 4 CH bonds, are produced. These electron pairs are shared by the carbon and 4 hydrogen atoms. It is important to remember that carbon is a tetravalent compound and one should always check for the fulfillment of tetravalency. In a covalently bonded molecule, like ethane, even though they have strong bonds within the molecule, the intermolecular forces between them are weak. Because of these weak intermolecular forces, ethane exists as a gas. Every day we use things that contain a class of compounds called hydrocarbons. Hydrocarbons are compounds that contain hydrogen and carbon. This lesson is about the versatile nature of carbon. and the classification of hydrocarbons. At the end of this lesson, you will be able to explain the vital force theory and its criticism, explain the versatile nature of carbon, define catenation, explain the tetravalent nature of carbon, define and classify hydrocarbons, and explain the homologous series. In the earlier days, based on the source, the compounds of carbon were classified into organic and inorganic compounds. In those days, scientists believed that organic compounds could only be produced by living organisms. They believed that organic compounds were produced under the influence of a vital force and could not be synthesized in the laboratory. This belief was shattered when Friedrich Wöhler, a German chemist in the year 1828, prepared urea from ammonium cyanate, which is an inorganic compound, without the aid of any type of force such as vital force. Today, over 10 million organic compounds are known, and this number is constantly increasing. This number is far more than the total number of compounds of all other elements put together. The existence of such a large number of organic compounds is due to the unique properties of carbon. The unique properties of carbon are tetravalency, catenation, and formation of multiple bonds. Let's focus on the first unique property of carbon. In order to complete its octet, carbon shares 4 electrons with other atoms, forming 4 covalent bonds. This is known as tetravalency in carbon. The next property is catenation, which is the phenomenon of self-linkage among identical atoms to form a long chain of molecules. Carbon exhibits maximum catenation when compared to elements like sulfur and silicon due to strong carbon-carbon bonds and tetravalency. Due to this catenation, carbon atoms can form various types of straight chains, branched chains, and ring structures, thus giving rise to a large number of compounds. For example, N-butane is a straight chain compound. 2-methylbutane is a branched chain compound, and cyclobutane is a cyclic compound. The last unique property is the formation of multiple bonds. Carbon atoms are capable of forming multiple bonds with other carbon atoms. The compounds of carbon, which are linked by only single bonds between the carbon atoms, are called saturated compounds. For example, methane, ethane, etc. Compounds of carbon having double or triple bonds between their carbon atoms are called unsaturated compounds. For example, ethene and ethyne are unsaturated compounds. Based on the structure of the carbon chain, hydrocarbons are broadly divided into 2 groups: open-chain hydrocarbons and cyclic or closed-chain hydrocarbons. Open-chain hydrocarbons contain carbon-carbon straight chains. They are further classified into 2 types: saturated hydrocarbons and unsaturated hydrocarbons. Saturated hydrocarbons are straight-chain compounds containing only single covalent bonds. These saturated hydrocarbons are also known as alkanes. Methane and ethane are examples of alkanes. Unsaturated hydrocarbons are the straight-chain compounds containing double or triple covalent bonds. Hydrocarbons with a double bond between carbon atoms are known as alkenes. For example, ethene. Similarly, hydrocarbons with triple bonds between carbon atoms are known as alkynes. For example, ethine. The compounds of carbon which contain a closed string of carbon atoms are regarded as cyclic hydrocarbons. They are of two types, alicyclic and aromatic. Alicyclic hydrocarbons are a category of carbon compounds which are in the form of a carbon cycle and contain 3 or more carbon atoms, thereby behaving like open-chain saturated hydrocarbons. For example, cyclopropane, cyclobutane, etc. The cyclic compounds which contain a single and a double bond at alternate positions and exhibit special properties are known as aromatic compounds. For example, benzene. Carbon compounds are categorized into various groups based on their functional groups. Carbon combines with many other atoms like nitrogen, oxygen, sulfur, and halogens, in addition to hydrogen. These carbons, which are bonded to heteroatoms, exhibit characteristic properties. Such a carbon atom together with heteroatoms is referred as a functional group. These functional groups impart characteristic properties to the molecule. When carbon compounds with similar functional groups were arranged according to the ascending order of the molecular weights, the difference between any two consecutive members of the series were found to be the CH2 group, and such a series is identified as homologous series. Let's consider the family of alcohols. The functional group in alcohols is OH. Methanol with a molecular formula CH3OH. Ethanol with a molecular formula CH3CH2OH. And propanol with a molecular formula CH3CH2CH2OH. We observe that the difference between methanol and ethanol and the difference between ethanol and propanol is by a CH2 group. Let's now analyze the characteristics of a homologous series. A general formula is used to represent a homologous series. For example, alkanes can be represented by a general formula CnH2n+2. In any homologous series, the difference between two consecutive members is a CH2 group. For example, in the family of alcohols, the consecutive members differ from each other by a CH2 group. The members belonging to a homologous series are prepared by similar methods. For example, methanol and ethanol can be prepared by the hydrolysis of methyl chloride and ethyl chloride with aqueous potassium hydroxide. A gradation in physical properties is seen as the molecular mass increases in any homologous series. For example, methane, ethane, propane, and butane exist as gases. Alkanes from pentane to dodecane exist as liquids, and higher alkanes exist as solids. So, with an increase in the molecular mass, there is a gradation of physical properties.
Hey, did you know that vinegar is also known as ethanoic acid?
I always knew it as acetic acid. Are you sure?
Actually, both of them are correct. To avoid such confusion between names of organic compounds, a standardized naming convention is followed all over the world. You will learn more about this system of nomenclature in this lesson. This lesson is about functional groups and the IUPAC system of nomenclature. By the end of this lesson, you will be able to define functional groups, classify carbon compounds based on the functional group present in a particular compound. Explain the procedure of naming carbon compounds using the IUPAC system. About 10 million organic compounds are known to exist till date. Fortunately, organic compounds consist of a few similar parts combined in different ways. This helps us predict how a compound that we have never seen before may react by comparing how other compounds containing the same parts are known to react. These parts of organic compounds are called functional groups. Functional groups are specific atoms, ions, or groups of atoms that have consistent properties. A functional group makes up part of a larger molecule. In organic chemistry, apart from hydrocarbons, there are other molecules where carbon forms bonds with other elements, such as halogens, oxygen, nitrogen, and sulfur. A hydrocarbon chain contains one or more atoms of elements other than carbon and hydrogen. These additional atoms are called heteroatoms. Therefore, a heteroatom is an atom other than carbon or hydrogen present in a hydrocarbon chain. Heteroatoms have characteristic properties that are independent of the length and nature of the carbon chain. Hence, these heteroatoms are also called functional groups. Compounds that have the same functional group undergo similar reactions. For example, when a piece of sodium metal is added to alcohol, it reacts vigorously and liberates hydrogen gas. This property is independent of the number of carbon atoms in alcohol, but is dependent on the functional group OH. Since we have such a large number of organic compounds, remembering each individual name is next to impossible. This is why a rational system of naming carbon compounds was developed. It was modified by the International Union of Pure and Applied Chemistry, IUPAC, and is followed all over the world. According to the IUPAC system of nomenclature, the name of an organic compound consists of a root word, a suffix and a prefix. The root word indicates the number of carbon atoms in the basic skeleton. The chains that contain up to 4 carbon atoms have special root words which are based on their common name. For chains that have more than 5 carbon atoms, Greek number roots are used as the root words. For instance, when there is 1 carbon atom in the compound, the root word is meth. In case of 2 carbon atoms, the root word to be used is eth. Similarly, if the compound contains 10 atoms of carbon, the root word is dec. The phrase which indicates the nature of a functional group in the molecule is called a suffix. There can be 2 types of suffixes, primary and secondary. A primary suffix is added to the root word to indicate saturation or unsaturation in the carbon chain. Hydrocarbons that contain double and triple bonds are known as unsaturated hydrocarbons. For saturated hydrocarbons, the primary suffix -ane should be added. Consider a molecule that has 2 carbon atoms. The root word should be eth. As it is a saturated hydrocarbon, the primary suffix -ane should be added to the root word. Therefore, the name of the molecule is ethane. Hydrocarbons containing double bonds are known as alkenes. For such hydrocarbons, the primary suffix -ene should be added to the root word. For example, for a molecule that has 2 carbon atoms, add the root word eth. If there is a double bond between the carbon atoms, add the primary suffix -ene. Hence, the name of the molecule is ethene. Hydrocarbons that contain a triple bond between carbon atoms are known as alkynes, and for naming such hydrocarbons, the primary suffix "-ine" should be added. For instance, a molecule that has 3 carbon atoms will have prop as the root word. If there is a triple bond between the 2 carbon atoms, add the primary suffix "-ine". The molecule is therefore named propyne. A secondary suffix indicates the functional group present in the carbon compound. The terminal "e" of the primary suffix is replaced by the second suffix. The table shows examples of secondary suffixes. For example, a molecule of ethyl alcohol contains 2 carbon atoms, so the root word is eth. It is saturated, so the primary suffix should be "ane". But as there is a functional group OH in the molecule, remove the E from the name of the molecule and add the secondary suffix "-ol". Therefore, the IUPAC name of ethyl alcohol is ethanol. Using the same set of rules, let's try to find out the IUPAC name of aldehyde. Take the example of a molecule of aldehyde. It contains 3 carbon atoms, so the root word should be "prop". There are no double bonds between the carbon atoms in an aldehyde molecule. The aldehyde molecule is saturated, so the primary suffix should be "ane". However, the molecule contains a functional group CHO, so a secondary suffix needs to be included in the name. Remove the E from alkane and add the suffix "-al". Therefore, the IUPAC name of the given molecule is propanal. Similarly, let's try to compute the IUPAC name of ketone. In a given ketone molecule, there are 3 carbon atoms. Hence, the root word should be "prop", and as it is saturated, the primary suffix should be "ane". However, there is a functional group C-double-bond-O, so you must remove the E from the alkane and add the secondary suffix "-one". Hence, the IUPAC name of the molecule is propanone. Now, let's write the IUPAC name of carboxylic acid. As per the given table, the molecule contains 3 carbon atoms. Therefore, the root word should be "prop", and as it is saturated, the primary suffix should be "ane". However, there is a functional group COOH, which means you need to use a secondary suffix. Remove the E from alkane and add the secondary suffix oic acid. Therefore, the IUPAC name is propanoic acid. The parts of the name that precede the root word are called prefixes. For example, in the compound cyclobutane, cyclo is the prefix that indicates the alicyclic nature of the compounds. If the compound is not alicyclic, the prefix is absent. Let's look at some examples of IUPAC nomenclature for straight-chain saturated hydrocarbons. The compound CH4 contains 1 carbon atom, so the suffix is meth. It is a saturated hydrocarbon, that is, the carbon atom is bound to 4 hydrogen atoms by a single bond. There are no double or triple bonds. Hence, this compound is an alkane. The IUPAC name is a combination of meth and ane, which becomes methane. C2H6 contains 2 carbon atoms. Hence, the suffix is eth. The carbon atoms are saturated with each having 4 bonds attached to different atoms. Thus, it is an alkane. The IUPAC name is ethane, which is a combination of eth and ane. The compound C3H8 contains 3 carbon atoms. Hence, the suffix is prop. The carbon atoms are saturated. Each carbon atom has 4 bonds attached to different atoms. Thus, it is an alkane. The IUPAC name is a combination of prop and ane, making it propane. The compound C4H10 has 4 carbon atoms, so its suffix is bute. The carbon atoms are saturated, with each having 4 bonds attached to different atoms. Thus, it is an alkane. The IUPAC name butane is a combination of bute and ane. Since C5H12 has 5 carbon atoms, its suffix is pent. The carbon atoms are saturated with each having 4 bonds attached to different atoms. So, it is an alkane. The IUPAC name is a combination of pent and ane, pentane.